Hello, everyone, and welcome to session number 62 of the Porous Media Time Talks. I am Chiara, and I am joined here today in the studio by my friend Sarah from Heriot-Watt University. We are part of Interpol Young Academy and organizing members of the Porous Media Time Talks. And with this platform, we aim at giving the opportunity to early career researchers to present their work to the Porous Media community worldwide. Without further ado, I'm going to introduce our first speaker today, who is Aronne Dell'Oca. Aronne holds a PhD in Environmental and Infrastructure Engineering from Politecnico di Milano. And between 2021 and 2023, he has been a Marie Curie postdoctoral researcher at the Institute of Environmental Assessment and Water Research in Barcelona. Aronne's research focuses on modeling of environmental systems, including the dynamics of uncertainty, and he's particularly interested in solid transport in heterogeneous porous media. Moreover, he has just been awarded with a very prestigious USC starting grant for the project MIPORE that will focus on reactive transport dynamics in rivers. So with this, I just leave the floor to Aronne. So please, Aronne, the floor is yours.
Thank you. Thank you very much, Chiara, for the introduction. And so today I want to talk about mixing in porous media, and especially how we can reconnect it with the concept of spreading. But before I start, I want to thank Professor Marco Denz, with who I did this work, essentially. And then to start, I want to give a brief outline of what we are going to see. So I want to give you the basics, very basics of spreading and mixing, and then the context where we are going to explore these two objects, and then why we can think of them as two enemies, in the sense that we are going to introduce the concept of apparent spreading and how it doesn't relate very well to mixing, and then how we can reconcile spreading and mixing, okay? So, very basic here, spreading essentially means that we want to measure the spatial extension of a solid plume. And here on the right, what you are seeing is a snapshot of a concentration field of a solute that is traveling through a heterogeneous flow field, okay? So spreading just wants to measure, for example, in the main flow, main direction, which is here left to right, the extension of this solid plume. While mixing wants to focus on the dilution of a solid plume. So here is the same concentration field where I just increased the local diffusion, okay? And what turns out to be is that there is more dilution in our plume, and also mixing, we can say that it deals with the erasement of concentration gradients, the homogenization internal of our plume, okay? This is, broadly speaking, the idea of spreading and mixing. Then, to give a little bit more of the context where we are working, I set myself at the Darcy scale, and especially Darcy scale in heterogeneous porous formations, where the heterogeneity is in the hydraulic conductivity. So the flow field is ruled by mass conservation, is a steady flow, so there is the divergency of the velocity, which is equal to 0. Then there is the Darcy flow. Here porosity is assumed to be equal to 1 for simplicity. And then a key part is that we do say, look, the hydraulic conductivity, we treat its logarithm as a spatially correlated random field. And two key elements are the variance of this spatial correlated random field, so this sigma square y, which is a measure of how the intense are the fluctuation in the hydraulic conductivity, and then the fact that there is a correlation in space. Here is an exponential correlation where Ly is a characteristic correlation length of the hydraulic conductivity. And we are looking to a big domain here, in the sense that we have many correlation length scale in the transverse direction and in the longitudinal direction. The flow is going to be left to right, and what you are seeing here is a color map of the logarithm of the magnitude of the velocity. And then regarding transport is governed by the advection dispersion equation locally. There is accumulation, there is advection, there is diffusion. Here I wrote it in terms of Peclet number, which is a measure of the intensity of advection over diffusion. And we are going to use a Peclet number of 100. So advection is an important mechanism in our setting. Okay, And then the initial solid plume is placed here along a line to simplify our life, and then we were letting it to evolve downstream in this heterogeneous flow field. And what we are going to get is something like this. Here I'm just plotting a few snapshots of the concentration field, where this tau A is an advective time scales, okay? But the key point is that our initial straight line gets distorted under the action of advections. So internally it gets stretched, and as it gets stretched, local diffusion can, over time, homogenize internally our solid concentration field. And then what we can say about this solid plume is, for example, why don't we try to measure its spatial extension? And a concept that is often used is the so-called apparent spreading scale. What is this apparent spreading scale? Essentially, it's nothing else than the spatial variance of the wall plume, okay? So it's a measure of the wall extension of the plume. This is just a formula, but it's just a variance, essentially. It's over the concentration field, spatial variance, and just in the longitudinal direction. X here is the main direction, this left to right. And so, once we have a variance, why don't we try to say that, look, could I simplify my life by saying that internally, my plume at each position can approximate it as a Gaussian bell. A Gaussian bell whose variance is this apparent spreading scale. So essentially, I could say, look, my concentration field, rather than being this complex field, I approximate it through a Gaussian approximation of Gaussian closure, and I insert my apparent spreading scale to get a measure of the extension of my Gaussian bell over time. And here in this plot, we are seeing how this apparent spreading scale grows as a function of time. And note that it is in log-log. And for comparison, there is the pure diffusive case, where essentially there is no perturbation in the flow field. Just diffusion is making my plume growing. And we can see that the two are quite close at the beginning, but then as the line gets, the solid plume gets distorted, somebody can go faster, somebody can go slower, and so there is a faster increase in the variance, apparent variance of our plume due to the flow perturbations. Late times, we recover a Fickian scale, meaning that at the late times, when it is well mixed, the growth of my plume can resemble a dispersive process, okay, since we get the same scaling, but with a clearly higher degree of dispersion or spreading. But what about mixing? Well, mixing, first we need a metric to quantify mixing, and one of the most used is the mixing state. What you do is essentially to take the concentration, you square it, and you integrate over the domain. And here, that mixing state is represented by the black curve, this solid, which is decreasing as a function of time, essentially because my concentration squared is decreasing. I am diluting this concentration field, okay? And as a reference, again, the purple is what you would get in terms of just pure diffusion. And we can see that here there is enhancement of mixing due to the perturbation of the flow. Why does that occur? Well, essentially because I am distorting my plume. I am creating these internal structures which increase the area, the internal area, over which diffusion can dilute my plume more efficiently. Then, coming back to our previous Gaussian closure using the apparent spreading scale, if I use this as Gaussian closure, I square it, and then I integrate it over the domain, I get this compact expression for the mixing state, which is telling me that, look, as the apparent spreading scale grows, the mixing state is decreasing. But when we go to check the numbers, we see that, yes, the scaling is more or less okay, the trend at least, but the numbers are off. If I use the apparent spreading scale to reproduce mixing, I am always diluting too much. Why is that so? Well, essentially because what I am saying with this type of model is that at each section, my concentration is represented by a Gaussian bell, but whose variance is too big. because this apparent spreading scale is more a measure, especially in the early times, of the distortion of my plume rather than the actual extension of the plume where I have solute. Okay, so there is too much dilution if I use the apparent spreading scale, and so the mixing is not well represented. So a way around of it is to say, look, why don't you treat, or why don't you think of your big plume as the sum of pointwise injections. These pointwise injections are called, you can call it green functions or lamella. And here, at this given time, I am zooming in over 3 pointwise injections, how they have evolved, and I am putting the centroid here, these red circles, okay, of these 3, and then the white centroids are where there should be other pointwise injections. And then for each pointwise injections, I can also measure the spreading scale of each of them. These double arrows, blue double arrows. This is the formula, but essentially it is just the variance of each of these small injections, okay? And then once I have the variance of all of them, I can average, okay? And so I get the effective spreading scale. The effective spreading scale is said to be effective because it's more effective in measuring the extension of the solute, taking out the internal distortion, okay? The extension of the solute plume if I take out the internal distortion of my plume. So that is way more related to mixing, because here we can see, for example, in terms of spreading, the gray curve is how the effective spreading scale is growing. So at the beginning, it coincides with diffusion, because it is just diffusion at the beginning that is making my plume to grow in the longitudinal, or to dilute in the longitudinal direction. Then there is the impact of flow perturbations, but that is less intense if I compare it to the apparent spreading scale, the dashed, the one that we saw before. Because the dashed here is more dominated by the early times by the internal folding and the internal stretching of my plume. And then, so what happens if I want to reproduce mixing? Well, the way that I can do it is, and this is termed effective dispersive lamella, the way that I can do it is to stick to a Gaussian approximation, but now I use the effective spreading scales rather than the apparent spreading scales. And I am able to reproduce mixing much more better, okay? This gray curve, I am capable of reproducing the dilution of my plume much more better once I measure the actual extension, if I follow internal my plume, the actual extension of where are my solute, okay? That's the key point. And then here you are also seeing this line with dots, which is just the dispersion of the centroids of the pointwise injection or Green's function. So, and you can see that these intermediate times, the apparent essentially coincide with the dispersion of the Green's function centroids, meaning that over these early times, the apparent spreading scale is more reflective of the internal distortion of my plume rather than the actual mixing process. Then at the late times, the two coincides because everything has been homogenized. Every pointwise injection is going to be very similar to the other. But then here is just few references in the literature if you are interested. But then what happens if I increase the heterogeneity in my porous media, in my geological formation? So here it is the flow field that we saw before, and here is the case where now I increase the variance in the hydraulic conductivity in its logarithm, essentially. And so what we can see is that the flow field gets more complex, but also it is covering more order of magnitude in the variability, okay? So there is more variability, there are more intense perturbation in the flow field. And the type of evolution in terms of concentration fields that we get is something like this, okay? There is more stretching, there is more distortion, there is more holes in our plume, everything is more complex. So once I try to use the effective dispersive lamella approach, I fail in the sense that the trend is okay, more or less, but the numbers do not match, in the sense that, again, I am diluting my plume too much if I use this type of approximation. And why is that so? And well, if we turn our attention to the spreading scales, what we are seeing here in gray is the effective spreading scales. And these red curves are the spreading scales of single point-wise injections, the concept that we used before. And we see that here, at these intermediate times, there is a huge variability in these spreading scales of the point-wise injection, meaning that, in other terms, the average maybe is not enough. And we can see it more clear here. If I zoom in, as I did before, over a region of my plume, and I check how point-wise injections are behaving, I can see that, look, these three have different spreading scales. The two of them are a lot stretched, and there is a lot of spreading, while for some of them there is not that much spreading. And so the average, the effective spreading scale, maybe is not enough to represent the whole distribution of, or the variability, the internal variability in my plume of the spreading scales. So we decided to propose this stochastic version of the dispersive lamella, where essentially you have to integrate over the distribution of the spreading scales of your point-wise injections, or lamella, or gain functions, call it as you prefer. So the average is not enough, but you need to recognize that, especially at the early times, there is an internal variability in the spreading process. And this helps a lot to fix the early times behavior. But at the late times, we are still off. And it's not a coincidence that the red and the gray curve, they do coincide, because at the late times, every point injections is going to approach the effective dispersive scales, okay? So the model is working well, but still we are missing something at the late times. So what we decide to do is to measure what we are missing. So we use this deviation factor, which is nothing else than the actual mixing state minus the mixing state using the stochastic dispersive lamella divided by the letter. And as a function of time, this is telling us that, look, you should dilute less, actually. There is something that you are missing in your model, which should allow you to dilute less your concentration field. And so far, we didn't say anything about the interaction between point-wise injections or Green functions or lamella. And if we go back to what we saw in the less heterogeneous case, here I am plotting, this is our 2D domain, at 3 times I am plotting the positions of 100 Green functions or 100 lamella, the red dots, and then the rhomboids are proportional to the spreading scales of each Green function. And then the effective dispersive lamella is essentially telling us, look, in the longitudinal, use this term, so use just the effective dispersive spreading scale, and that's good. This 1/L factor comes from the way we treat the transverse component, which essentially here we are saying that we preserve the initial concentration, or if you want, we do not dilute in the transverse direction. And this is the same of saying that, look, also in the transverse, you can use a Gaussian approximation, okay, and let each Green function to grow with effective transverse dispersive spreading scale. But since they are going in your model, they are all going straight, essentially when you do sum up this Green's function, you just preserve the initial concentration, the 1/L, okay? So the straight trajectories that you are assuming in your model, they are inducing the 1/L preservation of the initial concentration. What we did then was to test for the higher degree of heterogeneity, the stochastic. But in the stochastic dispersive lamella, essentially, you are playing with the longitudinal component of mixing. You are just saying that, look, why don't you try to consider that there is a distribution of spreading scales within your plume, but you don't touch anything in the transverse direction. But if we observe carefully this image, what we can see is that, look, in the transverse direction, we have clusters of Green's function. And we can clearly see that there is a focusing due to the flow focusing, which is pronounced when the heterogeneity is higher. There is the Green's function are brought close together, okay? So they are transported, they are conveyed within the same preferential flow path. And then over time, the trajectory get back to being straight. That's okay. But like if you scroll here, you can see that there is like a compression of Green's function position in the transverse direction. There a separation of them, then again compression, separation, and so on. Plus, there is also the mechanism of folding. Sometimes here you can clearly see that our Green's functions or pointwise injection has been folded one on top of the other. So what we want to do now is to get a phenomenological model for the transverse compression and separation and the folding mechanism. And we start with what we think is a small scale effect. So the compression and separation. And the way it works, this phenomenological interpretation, is that at the beginning, you have your 1 over L concentration distribution, okay? Every Green's function is at its own position. These are the centroids. And then the classical model would say everybody goes straight. But what if we assume, we allow for a pair of Green's functions to get separated, okay? These two red dots get separated, and they get separated over these scales, LS. The action over LS actually is to increase dilution, because you need to preserve the mass, which is confined initially between these two Green's functions. This actually means that you are diluting. This is not what we want. But what happens? It happens also that over these portions, these two Green's function, if they get separated, you allow for the interactions with the background, okay, with the others, which is here represented with this yellow, which is an increase in the concentration, so it's less dilution, and that scale with a scale of overlapping. So what we tried a simple model that says, look, a part of your deviation factor, a part of something that you are missing at the small scales can be written like a ratio between the scale of overlapping and a scale of separation. And then the scale of overlapping, you can rewrite in terms of the scale of separation. And now we need an expression for the scale of separation, which is just the average distance in absolute term between the centroids of pairwise Green's function in the transverse direction, obviously. And look, this is a good approximation of what we are missing in terms of mixing, okay? The orange is this separation compression that we just mentioned, and the black is the total missing contribution to mixing. But then the last piece of our model is the folding mechanism. The folding mechanism essentially is telling us, look, there is a certain initial scale that we call LF of folding, where the Green's function that are in these initial scales, they are going to be conveyed in the same flow path, okay? They're going to be folded inside this flow path, and you can clearly see it here. Here there is folding, and here there is folding. So what we do say, again, is look, there is a concentration, and on your folded ensemble of or set of Green's function, you can simplify them like considering a centroid here, separated by half the initial length of your folded segment. And then over time, you get an increase in the concentration due to folding, which behaves as something like this, because these two centroids are brought close together as a function of the dispersion of again, a dispersive or spreading scale of the centroids in the transverse directions. And then in the longitudinal, you do say the size of this folded line scales as the dispersion of the centroids of Green's functions in the longitudinal directions. Then this large scale folded associated deviation factor, you can write it as the product of these two contributions. One is very simple, the other is a little bit more complex. But the key idea is that, look, you can recover part of the mixing mechanism as you once you include the folding of your line, and we treat it relatively simple with this type of phenomenological schematizations. What we get now is this green curve, which match fairly good the total missing contribution to mixing. And then our mixing state now is this, according to our new model, is this green curve, which matches very well the actual mixing state, which is the black curve. Then additional material for study, if you are interested, is the lamellar description of mixing, where the author proposed a different approach to treat the interaction between lamellas or green functions. Then the conclusion here is that, yes, spreading and mixing can be reconciled, especially at the beginning through the use of the effective spreading scale. But then once you go to highly heterogeneous media, you need to account for additional interactions. And the information that you need, they can be retrieved from spreading and dispersive scales again. So spreading and mixing, and dispersion also if you want, they are not that separated, but if you play well with spreading and dispersive scales, you can reconstruct your mixing state. And then to conclude, I want to take the opportunity to say that we have some job offers for in the context of the recently ERC founded project that Chiara mentioned. And the goal there is to explore the processes of transport, mixing, and reactions in rivers, starting from the riverbed sediments to the scale of meters, so channel scales, and then up to kilometer scales. So if you are interested to it, just check at the site. Thank you.
Thank you very much, Aronne. Oh, it was a really, really nice presentation, really comprehensive. So if people in the audience have questions, please leave them in the chat. Right now we don't have any, so we'll start with some of my own. Well, so the first question I will have is, did you see any direct correlation between the spatial correlation length of your hydraulic conductivity field and then your effects on spreading and mixing of your CO2 plume, or solute plume, basically?
Yeah, I mean, we didn't check it, but it is clear that you can have like, where it is, like this guy, there is an influence over the, for example, of the effective spreading scales, that it is influenced by the correlation length of the underlying hydraulic conductivity. There are closed expression where using perturbation theory when the heterogeneity is low, or there are semi-empirical correlations when the heterogeneity increases, that has been proposed like in the last decade, more or less. But
Okay.
if you can have it.
All right, thank you. So then could you be interesting to just express every correction in terms of the spatial length for the hydraulic conductivity?
Yeah, I mean, everything can be normalized. So can be normal. You can here I just normalize time over the characteristic advective time, but you can normalize every spatial dimension using the correlation of the underlying conductivity field.
Okay.
That can be, yeah, can be, and it can also be useful. Yeah.
Yeah. And then my last question will be about uncertainties. Did you manage to see the effect on how the uncertainty on your spreading and mixing spatial variances affects again the plume, the solid plume? Would you be interested in quantifying these uncertainties? And if so, how do you manage to do this?
Well, one thing is here in this work is that the initial size of the plume is big. Big,
yeah.
You were saying big means big in terms of correlation length scales. So if I look to the evolution of a plume in this flow field, I will get something like this. But if I do the same exercise in another realization of the flow field, I will get something very similar. So since the plume is big, initially, there is not much uncertainty about apparent, effective, and mixing state if I get another realization. Okay.
All right.
Then if you move to small plumes, that the uncertainty about especially uncertainty about mixing, there is room for additional investigations.
Okay, great. Good to know. And what kind of application are you focusing with this work? Like remediation of soil?
These, I mean, once you get, this has been, you can see it as an aquifer if you want, cross-section of an aquifer or a planar view of an aquifer. And then once you solve for mixing, if you have fast reactions, that's enough to get the reaction rate over your plume. So it can be for remediation where there is some contaminant which react fast with pure water or water with a lot of oxygen. Then mixing is very important to get reaction properly, because mixing is telling you how much two reactants are going to be in contact or not.
Yeah.
So before you
it.
mix, and then you can solve for some type of reactions.
Okay, cool. Very interesting. Thank you very much. So Chiara, do you have any question for Aronne? Nope. So we don't have any from the chat either. So thank you again, Aronne, for this nice talk. And I think we can do the next speaker. Second speaker is Mahsa Shirazi. She is a PhD student in the Department of Chemical and Petroleum Engineering at Sharif University of Technology in Iran. And she is also a reservoir engineer at the Iran Central Oilfield Company. Research interests include surface engineering, petroleum, and polymer engineering. Mahsa couldn't join us in the studio for the live stream due to technical difficulties, but we have a pre-recorded video for a presentation that we will share with you today. So she will be presented on how to control surface characteristics in microfluidic experiments for fluid flow studies in porous media. So if you have any question for Mahsa, please write them in the YouTube chat or reach out to her directly, as there won't be any Q&A session after this recorded presentation. And all right, so enjoy Mahsa's talk then.
Mohani and Dr. Mohsen Masihi, and the consultant of Dr. Youssef Tamsi. Hello everyone, hoping you are well. My name is Mahsa Shirazi. I'm a PhD student at Sharif University of Technology under the supervision of Dr. Hassan Mohani and Dr. Mohsen Masihi, and the consultant of Dr. Youssef Tamsilia. I am also a reservoir engineer at Iranian Central Oilfield Company. It is my pleasure to participate in this conference. My presentation is about how to control surface characteristics in microfluidic experiments for fluid flow studies in porous media. It will begin with a brief introduction of the general concepts of this study, followed by the main objects, methodology, experimental results, and finally the upcoming works for the future. As you know, the simultaneous flow of two or more phases in porous media is a common phenomenon in most natural and industrial processes, such as groundwater movement in the subsurface, carbon storage in porous geological structures, enhanced geothermal energy production, and hydrocarbon recovery from subsurface reservoirs. The fluid displacement process could be affected by surface properties such as porosity and pore geometry, fluid properties such as viscosity ratio of fluids and surface or interfacial tension, surface fluid interactions such as wettability, and flow behavior including fluid dynamics and flow regime. Roughness and heterogeneity are among the most important surface characteristics that have been less attended. Although they have been investigated by some researchers both theoretically and experimentally, the majority of studies on the displacement process have been conducted for ideal plane surfaces because of the complexities associated with roughness. This is why most of the phenomena behave differently in the presence of rough surfaces. To investigate the role of surface roughness on the displacement process in a natural porous media, it is required to dynamically visualize the fluid flow behavior. However, most of the natural porous structures are usually opaque. For example, it is a sample of a natural core flood of an oil reservoir. As you see, it is an opaque media and the displacement process should be conducted in a core flooding apparatus like this. In this media, the dynamic visualization of the process is so difficult, and it requires complex imaging techniques such as X-ray microcomputed tomography. Despite the high resolution of the captured images by microcity, the speed of capturing is extremely low, and the required time for scanning the media surface is usually as long as several minutes to several hours. So, it is only able to extract static images of the inner structures, and the dynamic visualization only occurs when the fluid velocity and the scanning time are very slow. According to the main problems associated with opaque media, we can use a type of transparent microscale media such as interconnected porous network micromodels instead. As you see in this picture, it is a schematic of a micromodel made from glass. The experimental setup of the micromodel is a simple collection like this, which only needs a syringe pump alongside a set of transmission microscopes and cameras for optical visualization. You can see a sample of dynamic visualization in this micromodel, which is easily captured during the displacement process. It should be noted that as these structures are usually made synthetically, it is required to make their surface characteristics similar to the natural porous structures. To investigate the role of surface roughness on fluid flow behavior in transparent media such as micromodels, different degrees of roughness should be artificially created on the surface. One of the related researches on this topic is the study by Mehmani et al. In 2019. They fabricated 4 different glass micromodels with the same pore geometry and different degrees of pore surface roughness from very smooth to very rough. They conducted drainage process experiments of oil and gas displacement to assess the impact of surface roughness on the flooding experiments. They used the photolithography method for micromodel fabrication. These are the steps of roughness creation. The desired depth was created by etching with hydrochloric acid, and the desired roughness was created with a glass etching cream under different exposure types. These are the SEM images of the roughed surfaces they have created. They defined a roughness parameter named omega as the ratio of the average helix height to the pore depth. Based on their experimental results, the omega parameters less than 5.5% have no significant effect on sweep efficiency, while the higher values of 12.5% significantly increase the sweep efficiency and postpone the breakthrough time. As it is obvious from the introduction part, the main purpose of this study was to investigate the role of surface roughness and heterogeneity as 2 important surface characteristics. As we know, roughness could naturally exist in the surfaces such as core plugs, or can be artificially created on the surface. Our purpose in this study was to artificially create roughness in transparent micromodels. Surface heterogeneity can result from different mineralogy, different wettability, or different roughness distribution, which is the purpose of this study. Different types of etching methods were used in this study to create roughness on a plain glass substrate. The purpose was to analyze the impact of etching methods as well as the impact of high temperatures on surface topography, chemical composition, roughness, and etching depths. The materials that we used for the experiments were soda-lime silica glass plates, commercial glass etching cream, hydrochloric acid, and hydrochloric acid. The methods of roughness creation are introduced here. The first method was laser ablation, in which a target pattern was laser engraved on a glass surface. The surface was then completely washed with hydrochloric acid to remove the remained glass shards. The second method was cream etching, in which the target pattern was drawn on a stencil and it was adhered to the glass substrate and a layer of etching cream was applied to it. The glass surface was then washed under a water stream and the stencil was removed. The third method was the combination of laser ablation and etching cream. The procedure was same as the etching cream, except for using a laser engraved substrate instead of a plain surface. The last method was hydrofluoric acid etching, with the same procedure as etching cream, except that instead of putting etching cream on the surface was completely immersed in hydrofluoric acid. To characterize the fabricated surfaces, the FESEM and EDX analyses were used for the characterization of surface topography and chemical composition. The profilometry analysis was used for quantitative and qualitative measurements of surface roughness and etching depths, and the AFM analysis was used for surface topography and roughness measurements values lower than 2 microns. For the profilometry analysis, the roughness is measured using Guidon software. The outputs are these parameters, including average roughness, which measures the average deviation of all points' roughness profiles from a mean line over the evaluation length. This image shows the procedure of etching depth calculation with the software. To analyze the impact of high temperatures during the bonding step in micromodel fabrication, an electrical furnace with a predefined automatic program shown in this table was used. Based on the experimental results, the FESEM images of different surfaces before and after exposure to high temperature are shown here. As you see, in the laser engraved surface, a homogeneous rough topography was observed, which is attributed to the layer-by-layer ablation process of the method to physically engrave the surface with a regular pattern. In the surface etched by etching cream, a homogeneous rough surface was observed attributed to the presence of sodium bifluoride and ammonium hydrogen difluoride in the cream that chemically reacted with the surface, according to these equations. The reaction strength was so low and led to an indirect liberation of HF with a corrosive nature to create a low degree of roughness. The FESEM image of the laser engraved surface etched by cream also showed a homogeneous rough topography. In the glass substrate etched by hydrofluoric acid, a heterogeneous rough topography was observed, as hydrofluoric acid might react differently with different parts of the glass substrate, based on this equation. The commercial reaction of hydrofluoric acid with the surface is so stronger than that of etching cream. In both cases, the reaction products were soluble in water, and consequently, the fluorine element was not observed in the EDX analysis. In all surfaces, high temperature has no significant effect on surface topography, except for etching cream and combination of laser and etching cream. It seems that the effect of etching cream disappears under high temperatures. According to the results of EDX analysis, the chemical composition of all etched surfaces are approximately similar to the plane surface. Moreover, exposure to extra high temperatures didn't significantly change the surface chemical composition, which is obvious in the silicon oxide contents of all surfaces. The profilometry analysis for surface roughness of different substrates before and after exposure to high temperature are shown here. In the laser engraved surface, a high roughness value was obtained, which was attributed to the creation of regular peaks and valleys on the surface. In the surface etched by cream, a low roughness value in the nanometer scale was observed, attributed to its weak chemical reaction with surface. In a laser engraved surface etched by cream, the surface roughness was reduced compared to the laser engraved surface. This might be attributed to the reduction of the created sharp helix by chemical reaction of the etching cream. In the surface etched by hydrofluoric acid, an intermediate roughness value was observed. Considering the strong chemical reaction of hydrofluoric acid with the glass surface, the obtained roughness was dependent on the exposure time with acid. Similar to the results of the FESEM, temperature has no significant effect on surface roughness except for etching cream and combination of laser and etching cream. The roughness variation in a laser engraved surface could be also shown by calculating the roughness values in 4 square sections of the two-dimensional profile, as illustrated in this figure. As it is obvious, the roughness values are approximately similar in the 4 squares, confirming its homogeneous distribution in a laser engraved surface. In a surface engraved by a combination of laser and etching cream, again, the roughness values of the four squares are similar, confirming the homogeneous roughness distribution. However, in a hydrofluoric acid etched surface, a significant difference is observed in the roughness values of four squares, confirming the heterogeneous roughness distribution. In this slide, the profilometry analysis of the etching depths of different substrates are shown before and after exposure to high temperature. As it is obvious, the temperature effect was similar to previous experiments. As I mentioned earlier, in the hydrofluoric acid etching method, the degree of roughness and etching depths are strongly dependent on the exposure time. In this figure, you can see the graph of depths versus different exposure times to hydrofluoric acid. As it is expected, the longer exposure time leads to a larger depth, because the surface is more corroded with the hydrofluoric acid. This figure shows the graph of surface roughness versus different exposure times to hydrofluoric acid. The trend is increasing up to reaching a maximum roughness value and then decreasing. This may be because of the nature of this method, as hydrofluoric acid reacts differently with different parts of the glass. A comparison of different etching methods is given in this table. As I mentioned, hydrofluoric acid is a flexible method in which we have complete control over the values of roughness and etching depths by changing hydrofluoric acid concentration, exposure time, and etc. The roughness distribution in all cases is homogeneous except for the case of hydrofluoric acid, which is heterogeneous. The effect of etching cream almost disappears under the extra high temperatures, making it unsuitable for use in micromodel fabrication applications. These are the upcoming works that you consider for the future. The first and the most significant one is to investigate the role of surface roughness heterogeneity on two-phase fluid dynamics, including porous slope trapping mechanisms, phase connectivity or breakup, flow regime, fluid saturation, phase recovery, and etc. The second plan is to investigate the simultaneous role of surface roughness heterogeneity and aqueous and non-aqueous phase properties on two-phase fluid dynamics. And the third plan is to present a modified version of the Lenormand plot. These are some important references of this study. Thanks for your attention and welcome to any questions.
Awesome, very nice presentation, very interesting outlooks as well. So I hope you enjoy it. Again, feel free to leave questions in the chat for Mahsa. So from now, we will conclude the session. Thanks again to both our speakers for sharing their research with us today. And we would like to advertise our next month session. Thank you. So scheduled on the 12th of November at 3:30 Central European Time. So we will have two speakers, Hao Shi from the Harbin Institute of Technology in China and Happiness Imutinian from the University of Porous in France. And finally, so this is us. If you have any comments, want to be involved as speakers, or subscribe to our mailing list, you can contact us at porousmediattt@gmail.com. And yeah, thank you everyone. Stay tuned and see you next time for the Porous Media Tea Time Talk. Bye.
Bye. Bye-bye.